All right, so we left it here in this code, and I remember if I run this that it was kind of okay. I did not I did not understand fully. So 108 and false, and that I actually just yeah um, that's what the model expected as well, which is good. Now I remember there's one thing which I was not happy with, which is um, the function to calculate generators, right? So the fact that it's just picking these as generators, and I'm not sure I follow the logic. So that is potentially a place for mistakes. But for the sake of like, I'm gonna try to remember these. So this is definitely one thing that is a blind spot that I want to make sure that I dig into later. But I kind of really want to start to bridge towards the the next step, which is now we have G. Okay, so now we have G. So that's G. So having G, I guess we now can step into the stuff that I like, which is unknown territory, which is let K be a large enough field with characteristic 2. So a large enough field with characteristic 2. Let's break this down. Let's open, I'm going to open another conversation in here. Or let's do let's do it. It somehow works better if I just go or it's fine, yeah. And then start, and I will say, okay, so how can I represent fields in SymPy, and specifically field of characteristic 2. And also, what does it mean that it's large enough? This is always also like, this doesn't sound very mathy. Large enough field with characteristic 2. I guess large enough to have a block at all, or whatever that is, right? So you can represent fields and work with finite fields, including fields of characteristic 2 like F2. So first of all, what is a field of characteristic 2? And what's the characteristic of that field? Maybe something like dimensions. I think we talked a bit about this. You see, the problem is this. I like this, don't get me wrong, but I have the feeling that those things are too long. Okay, so where was I? Here. The characteristic of a field is a fundamental property that describes the behavior of addition. Okay, in the field. Specifically, it is the smallest positive integer n, such that adding the multiplicative identity 1 to itself n times yields 0. So that's basically, yeah, okay, but that defines in a way a modular behavior, right? If no positive integer n exists, the field has characteristic 0. Okay. If such an n exists, because is the smallest n, and it must be a prime number, because fields are integral domains, no zero divisors, and must divide by integer k. So a field of characteristic 2 is a field where the characteristic is 2, meaning 1 plus 1 equals 0. The additive inverse of 1 is itself. 1 equals minus 1. Examples. F2, the finite, so elements 0, 1. Addition 0, 0 equals 0, 0, 1. Yeah, so the binary numbers, right? No. Addition, multiplication. Oh, no, okay. It's arithmetic module 2, yeah, exactly. Finite field extension. So for n bigger than 1, the field 2 to the power of n has 2 to the power of n elements and is constructed as a quotient of the polynomial ring F4 with element 0, 1, alpha, and alpha plus 1, where alpha plus 1 equals 0. Arithmetic is performed modulo the polynomial. Okay, that is too crazy. But okay, so we know we don't want to get, but now let K be a large enough field with characteristic 2. How many blocks does KG have? Now let's understand, how do we construct KG? How do we construct KG? If we have a group, a defined group G, and a field F of characteristic 2, what's the interpretation of KG? A group algebra. Essentially it means, or group ring, okay, of the group J over the field F. Fg, where F is the field of characteristic 2, often denoted K in this context of brevity. G is a group. So I'm going to start combines the group G with the field F. So formally, I mean, okay, so but essentially what takes precedence seems to be the group, right? Because it's just basically adding addition to the group. So below, I'll explain the concept of group algebra. Yes, so structure combines the group G with the field F as the vector space over F with a basis indexed by the elements of G. Okay, so G is taken as the basis of the algebra, or the elements. That is, the elements of Fg are formal linear combinations of the form AGG, such that AG belongs to F and G belongs to G. Linear combinations. So here's where we're just, it's kind of like, okay, so we're adding, we're doing, well, you're doing pairs. In our case, of course, if it's characteristic 2, we know that there's basically 2 elements, right? That's what I would say. Characteristic 2 has 2 elements that, no, I don't know. Yeah, maybe. No, it doesn't have to have, it has multiple elements. It doesn't have to have 2. But if you add, yeah, because 2, if you add 2 if you add 2 of the elements, you get 0, right? I know the identity, okay. So now we just have to apply this extra rule, right? Vector space structure, the elements of G. G is finite. If G is finite, the dimensions Fg over F is just G. The order, okay, so G is really used as the basis, and so as the dimensions. The order of the group is then the dimensions. If G is infinite, it's an infinite dimensional. Add 2 elements by adding coefficients for each group element. Okay, so it's essentially AG, BG. You just add addition, basically. Vector space structure, scalar multiplication, algebra structure. the multiplication in FG extends the group operation in G. Okay, so even multiplication. So you really get an algebra. What's the difference between a group, a field, and an algebra? And do this relate? Be brief and high level. So a group is a set with a single operation. A field is a set with two operations, addition and multiplication. Okay. And an algebra is a vector space over a field equipped with a bilinear operation like multiplication that defines how vectors combine. Often generalizing fields or rings. Groups focus on one operation, fields are a second operation, and algebra is built on fields by introducing vector space structure. So what is it that's special about adding vector space? I mean, what's vector space in the first place? The vector space is just the vectors. It's just vectors, right? Vectors and their operations, right? Versus a scalar. I guess that's so essentially an algebra just introduces vectors. So it moves beyond scalars, right? Okay, so it's a set of elements called vectors over a field, so the real numbers. Okay, so it's something that is defined over a field, which is basically a field is just on the scalars. We can add vectors together and scale them by elements of the field. It adds scaling. It adds scaling to the whole thing. Yeah, 2D vectors over the real numbers. Adding a vector space structure to an algebra means you're not just working with a set of operations, but also with a framework where elements can be scaled and added. That's exactly scaled and added like vectors. This allows for linear combinations, enabling geometric interpretations, coordinate systems, and tools from linear algebra, matrices, transformations. I never thought about this way. It's special because it bridges algebraic operations like with geometric and analytical techniques, making algebras powerful for applications in physics. Essentially, an algebra is when you're adding and defining operations on kind of groups of scalars, right? However you want to call those groups, and that's the wrong word, but like collections, right? Because I don't want to sound confusing. But yes, so essentially, but why does now my question is why does the combination of a group and a field yield an algebra and not just a field? Combining a group and a field doesn't automatically yield an algebra. It depends on how they are combined. Okay, that's an important thing then, because here we're not really, it's not really telling us what it is, right? And I don't know why so this guy, so Grok is sort of assuming that we're having a group algebra. A field is already a structure with two operations, where the set forms an additive group and a multiplicative group. A group alone with one operation doesn't inherently produce an algebra when combined with a field unless you introduce a vector space structure over the field, along with a bilinear operation like multiplication of the vector space. That's how you get an algebra. Okay, so how? But so if I have, oh, maybe the reason this happens is because it's because of the nature of G. G is like the elements of G are actually tuples or vectors, right? You have collections over field. That's why. Like if, I think that's why in most of the cases, that's why you have then a resulting algebra, because you actually have to have those structures. All right, makes sense. How do I remember this? This is interesting. These are interesting concepts, right? You have groups, you have fields, and then you have algebras. I mean, those are just putting names on things that should be intuitive, right? Anyway, let's be tactical about these and use the time efficiently. So we now understand a bit more about these, and I think what I want to try to understand is what are blocks. Okay, fine. We can figure out how to define a group algebra. So that's something that we'll let the grok do. I guess the characteristic is just gonna add another rule that is gonna help us define that group algebra. Now, how do I know how many blocks does a group algebra has? How do I know how many blocks does a group algebra have? You need to consider the representation theory of G over K. The number of blocks corresponds to the number of block idempotents in the center of the group algebra, and it depends on the characteristic of the field K. Okay, so it actually depends on K, on the characteristic, which is 2. It's a vector space over K with basis elements corresponding to the elements of G, equipped with multiplication induced by the group operation. Okay, blocks. A block of Kg is a minimal two-sided ideal. It's a minimal two-sided ideal that cannot be decomposed further. The number of blocks is related to the number of indecomposable projective modules, or equivalently, the number of central primitive idempotents, the center of Kg. Okay. Identify the field and its characteristic. We know it's 2. Case 2. Okay, so it's as that simple. Wait, I mean, if the characteristic is 2, if it is P, and P divides the order of G, the group algebra Kg is not semi-simple, and the blocks are the P blocks of G. And I think that's the case, right? Because the characteristic is 2. I mean, we'll of course try to understand why, right? We will, I promise I'm going to try to understand why. The number of blocks is equal to the number of P regular conjugacy classes, blah, 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 blah. Alternatively, the number of blocks equals the number of P blocks. Is then blocks just this? Is so. Are algebra blocks, or is the concept of blocks in a group algebra a parallel to the center order of a group? It's a minimum two-sided ideal group algebra cannot be decomposed further into smaller two-sided ideals. Primitive central idempotents of the center in the group algebra. It kind of almost feels like blocks are particularly significant in modular representation theory. What does it mean? The primitive central idempotents of the center Z, e.g. of the group algebra. Help me unpack these, please. What are central idempotents? The definition of center is the same thing, right? It's similar. So it's the elements in kg that commute with every element of kg and the multiplication. What's more, it's even using multiplication, which is then the equivalent of the operation in the group G. In kg, an element x is the center, commutes with every basis element. Okay. A key fact is that it has a basis given the class sums, which is sums of elements in each conjugacy class of. Okay, that's getting too complicated. And an element E kg is idempotent if it satisfies that E squared equals E. So modular by itself gives back E. Projections into subspaces or components of the algebra. For example, in a matrix algebra, idempotent matrix P satisfies P squared equals P. And a central idempotent is an idempotent element EKG that lies in the center. And this means it's idempotent are crucial because they generate two-sided ideals in an algebra. If E is a central idempotent, the set KGE is a two-sided ideal. What is an ideal or two-sided ideal in this context? But essentially, if so, the blocks are the P blocks of G. What are the P blocks of G? Is a minimal, okay, definition of P blocks. Is a two-sided ideal. Central primitive idempotent. Okay. So we need to identify this primitive idempotence, I guess. But actually, wouldn't that mean that if this is what it satisfies, wouldn't that mean that in the case of P equals 2 is every single element? Okay, so these are blocks in that sense because alternate equals number of central primitive idempotents in the effect group. That's a lot of new stuff. Check if P divides by the order of G. Then proceed to analyze the P blocks as KG is not semi-simple. Computational tools. For complex groups, use software like GAP or Magma to compute P blocks. Okay, interesting. So what is GAP or Magma? Are these free? Groups, algorithms, and programming is an open source computer algebra system. Interesting. Okay. GAP. Learning GAP. Can SymPy do it? Can you calculate groups? Can you calculate blocks of an algebra with SymPy? Let's see. I'm gonna try to give it a shot. I'm gonna try to do because now we've decomposed enough of it. If I go back here, where do I have my code? Okay, no, that's okay. Okay, so we've got F elements in F1, F1. Does this really run like that? 0 mod 2, 1 mod 2, 0 mod 2. Interesting. Actually, it prints mod. FF, import FF. Field of characteristic 2. Okay, of characteristic 2. I mean, you can do this. It's all right. I just want to see if having breaking it down to that point sorry, helps me helps me here. So we have this program. Can we add so let's add a field of characteristic 2 called F. I don't know if that was actually stop. I don't know. So take the code and extend the code in order to add a field of characteristic 2 and then compute the group algebra FG export. So I really need to be more specific because there's so much context in here. I think it's taking a look at all this context, and I'm a bit afraid that it just gets distracted with these. Yeah, okay, that's fine. Use these. Over F. Still thinking too much before actually doing the code. As in like it's not computing it using SymPy, but that just might be a problem with SymPy. I'm currently looking for ways to find the field F using SymPy, which has GFP for finite fields. Does have built-in group algebra class based on recent searches. We might need to kind of move beyond that. So we might need to actually use these gap packages, installation, macOS. Run a few tests. Okay, there's a front end. There's the Gap app, which is a front end for these. And I'm praying that Grok knows about it. Okay, I don't know. Okay, so I actually can't install Gap. Yeah. Or additional packages. So it kept that like these. Define a simple group algebra class. Dimension elements. Let's see what the elements are according to these. Can I render the element? Can I add a print for the elements of FG to the code? I think I might have to install gap though to be sure. But okay, I don't really. I think it's enough if I understand what the concept of the blocks are, because computing it just seems like, you know, it's worthless to learn necessarily the steps, but it's like just let it compute, right? We have the tools, but I want to understand what the blocks are really in detail. Okay, so it's gonna print the elements now. I just want to make sure this makes sense at all, right? Oh, whatever. I have no idea. It could be. It could be, to be honest. To be honest, I have absolutely no idea. I don't know why some elements have higher dimensions. Some of them seem to have 6 dimensions. Why that? Why do some elements seem to have some vectors seem to have 3 components versus others 6? Is this normal? That's what I'm not so sure about. I think Simpa is not going to cut it. I think I need to get out of the environment here and install something on my computer. That's what I'm going to do in the next session, because I want to try one thing though. I'm going to try one thing now. See if I can get it to output the right question, because I know the right answer was 5. When I tried initially just copy pasting these, I was like, you know, it got it wrong. I think it said 2 or 3. No, that's the wrong answer. That's not the point. That's not what I meant. Okay, knowing, so having the code you have and knowing what we've explored in the context of this project, can you tell me how many blocks FG has? Let's see if now, like, having kind of helped the model build these together, it's maybe easier for it to understand, to reason and see that it's 5. I mean, that would be interesting. if it actually does. But yeah, while it's thinking about this, gap. How do I install this? Download gap, the app plus gap. Okay, great. I can just download that. Now accept. Status beta. It's actually searching in Mass Exchange group. That's crazy. But it might actually get it, because we have some more intermediate results, and maybe there's less chances that it makes a mistake, you know? Okay, so it's downloading actually. Okay, it's downloading. And then we'll close all these. Close. It's thinking, so we'll just go to grok.com. Do you know how to code a group, a field, and the FG algebra resulting of it using gap? Not do you know, but just code. I mean, this is what it's been saying. So let's see if it says if it spits out 5, I'm gonna lose it. It definitely didn't get it right, so it didn't solve it the first time. Come on, you can do these. It's actually looking at, thinking at gapsystem.org and blah 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 gapsystem.org. Okay, cool. So it's, to be honest, it's quite interesting how much of searching it actually needs to do. Cyclic group 4, define the field F as the finite field with 5 elements. What? Ah, okay. And a group ring. Really? Is that simple? Is that simple in gap? Come on. Come on, come on, come on, come on, come on, come on. Come on. Come on. You can do these. You can do these. You can do these. I mean, that was fairly simple. So let's wait until it actually downloads this, and then we'll continue. You can do these. Okay, I'll mute myself for a second. I'll be back and see what happens. Okay, because I need to go get some drink. Okay, I'm back, but it's still thinking. Still. So let's start from the group up, from the ground up, keeping things in two different buildings step by step. Imagine dealing with a group G, like the symmetries of a square. A group algebra over field K, say the complex numbers. It's like turning the group into a vector space with multiplication. Think of it as a toolbox where each group element is the basis vector. Yeah, exactly, intuitively. So you have G and E is the identity group. Then the group algebra KG consists of expressions like 2E plus 3A minus pi B. Okay. Now blocks come into play when you want to decompose this algebra into simpler pieces. Intuitively, blocks are like the irreducible chunks of building blocks of the group's algebra that can't be broken down for the everyday analogy. Yeah, okay, we don't need that. That's a little too much. Sugar coating. Blocks shine brightest in modular representation theory, where the field's characteristic divides the group's order. The field's characteristic divides the group order, working order prime field. Here things get defective or more complicated than over C, where everything decomposes nicely via Masheki's theorem. So a little bit more structure. The group algebra KG is a ring algebra over K, and we can think of this as its semi-simple case first, when the characteristic of K doesn't divide. Why is that the simplest case? And you're still thinking, boy, huh? You're really still thinking. Okay. Each matrix algebra is a block in a loose sense. They are the primitive central idempotent images, but blocks are more about the idempotent summons when the algebra isn't semi-simple. It still isn't, and I still can't break it down in my head. Into these chunks because of the P co-regular part influences how reps interact. Let's think about this. What does it mean to break an algebra into simple blocks and into more irreducible blocks? Into simpler pieces. Can you use a more known algebra as an example? Can we use something like modular arithmetics as an example? Something like these. Okay, wait. Yes, it is normal. The vectors you're... What? You thought for 9 minutes and you gave me the wrong answer. What? Fuck, man. It completely messed it up. It's not, I was not even at all able to understand what I was asking it. It thought for 10 minutes and it just like got confused with the question above. I think that's the problem with the context in here. I think that's just not helping us. There's too much context in these. And I'm going to try to do the following. I'm going to download these code. And I'm going to... And I'm going to copy these. And I'm going to create a clean chat. Even not with a file, like code. I'm going to copy the code actually. And I'm just gonna let it run, okay? And I'll comment later on what did grok speed in here. So expert mode, goaded, and I need to think about blocks. I have to go now. But yeah, I'll let this thing thinking, and then and then see what happens. See if that has helped or that helps at all. Like I just kind of cleaned up at least the context in the chat. It seems to, maybe I have to take the settings because it seems to kind of just consider everything that I've been talking about recently. Not even, you know. So yeah, it's fine. Let's I'll leave it like this, and then we'll see. Bye bye.